Right. This tutorial is going to talk a little bit about what is KSP and what are some of the things that we could be asked to do related to KSP. Really, KSP is just what we've been talking about, right? We've been talking about equilibrium, right? Where generically speaking, right, it's where the rate forward, right, A plus B going to C is equal to the rate reverse. We have dynamic equilibrium. There's no net change in concentrations, even though there is movement going on. For every one C that converts to A and B, we have one A and B converting to C. So there's no net effect. And as we learned, it's going to be products over reactants raised to their coefficients. So all my coefficients are 1 right here, and that's why they're all raised to the power 1, which we don't write. Then we started to talk about specific instances, right? And we introduced this Ka idea. Ka is still equilibrium. It's still forward direction is happening at the same rate as the reverse direction. So there's no net effect on the concentration of HA, A minus, and hydronium. But now what we're talking about is a very specific case scenario. And so we use a subscript to say, hey, we're talking about acids dissociated in water, right? Where it will always have this format because we're talking about a very specific context, right? So that's what KSP is. KSP is still equilibrium, where the rate forward is equal to the rate reverse, but we're going to talk about a very specific concept and context. And so this case is solubility product. We're basically talking about solubility. How well does a compound dissolve in water? Now, we have two case scenarios. We have ionic compounds dissolving in water. And what we know about ionic compounds is whatever does dissolve also dissociates. So if we were to write a KSP reaction for an ionic compound, it always takes this format. We have the undissociated, undissolved solid, and we have the relationship to the ions that are in solution dissociated. And this is what your KSP expression is always going to take the format of. You're going to have KSP is equal to the concentration of products over the concentration of our reactants, but because we're specifically talking about an ionic solid dissolving, there will be no denominator because, as we know, solids are not expressed in our equilibrium expressions. So we should be able to write lots of different equilibrium reactions and expressions for ionic compounds because it always takes this format, just as Ka always takes that format. Now, if it is molecular, remember molecules other than acids, when they dissolve, they do not dissociate in water. So you'll see here, here's my solid BZ, and it's in equilibrium with BZ that dissolves in water. But I'm not ionizing BZ because it's molecular. And when molecular things dissolve in water, they don't ionize, right? So an example of that would be sugar. If I had sugar, right, C12H22O11, and I try to take some solid sugar and put it in water, a certain amount of sugar will actually dissolve, but we're not going to see this molecule dissociate. We're just going to see one molecule of sugar separating from another molecule or many molecules of sugar, but the sugar retains its structure. So if we look at some examples, right, here's an example of an ionic compound, and we're asking ourselves, when this ionic compound dissolves in water, what extent does it dissolve? And again, what ionic compounds do when they dissolve is ionize. So here you can see that XY goes to X plus and Y minus pattern. And so if we were to write our equilibrium expression here, we would say that KSP is equal to the concentration of the cation times the concentration of the anion raised to its coefficient, right? If we look at this relationship, this also is ionic. Cobalt is a metal bound to a group of nonmetals. So if I'm going to write that reaction out, right, I have that cobalt. I have this polyatomic ion. And when I dissolve ionic compounds in water, there is going to be an equilibrium between that solid and the dissolved and dissociated ions. And in this case, I end up with 3 cobalt ions, each of them having a charge of +2. And I have 2 polyatomic ions that have a charge of 3. So if I were to write my equilibrium expression for this reaction, then I would have KSP is equal to the concentration of my cobalt ions raised to the 3rd power times the concentration of this ion raised to its coefficient, which will be the 2nd, right? So given that this is what our equilibrium expressions look like for ionic compounds, again, if I want to generalize it for ionic compounds, right, the KSP of an ionic compound, the expression will always look like cations concentration raised to its coefficient times the anions concentration raised to its coefficient. Because the KSP reaction that you're considering is some cation, right? Some cation bound to some anion. And in this case, I'm going to make that anion need 2 of them to balance the charge on that cation. And that solid is going to dissolve, and because it's ionic, it's going to dissociate into cations and anions. And that is what we're writing on our equilibrium expression. This is the reaction to consider. So let's go back. What do we do with this kind of information? And I will say, you'll see that I mostly talk about ionic compounds because that is 9 times out of 10 what we're asked to consider. So they'll either give you the molar solubility, which is how much of this dissolves in water. And they're telling you that 0.016 moles of this will dissolve in 1 liter. And so if we consider the stoichiometry of reaction, right, for every one of these that dissolves, I get 1 of these. And if this is how much dissolves, then that means I'm going to have a concentration of 0.016 molar. But look at the coefficient here. For every 1 lead chloride that dissolves, I am actually going to get 2 chlorides. So what I will see here is I'm going to have 2 times that 0.016 molar. So generally, if they give you the molar solubility, what the question is what is the KSP of this solid, right? And so now we can put those concentrations in and answer that question, right? Our lead ion concentration, when it's in equilibrium, is going to have a concentration, a maximum solubility of 0.016 molar. Our chloride concentration, because of the stoichiometry, is going to be 2 times that 0.016 molar. And we're going to have to square that because that's what we do with equilibrium expressions. We raise them to their coefficients. And so now we can simplify this and we can find what the KSP of lead chloride is. And most of KSP values are at 25 degrees Celsius. So if I take my 0.016 and I'm going to multiply that by 0.016 times 2, and I'm going to square that quantity, I get a value of 1.6 times 10 to the negative 5th. All right, so that's the first thing we could be asked. We could be asked, what is the KSP? That is the question. They will have to give you the molar solubility in order to answer that question. Scenario 2, they want to know what is the molar solubility? How many of these dissolve? And what they'll give you in this case is the KSP. And so in this scenario, give myself a little bit more room, right? We know the KSP expression, right? Because we can write that. What we don't know is the solubility. So what I do know is that cobalt's concentration is going to be 3 times whatever the solubility is. Because for every one of these that dissolves, I will get 3 of these. So what I tend to say is in here, I'm going to say there are 3 X's and I've got to cube that, right? And then for this one, it's going to be 2 times however many of these dissolve. So I'm going to say 2x, and then I have to raise it to the 2nd power because the coefficient is 2. So now I try to simplify this, right? 3x cubed is actually 27x cubed. And then 2x squared is actually 4x squared, right? And now I can simplify that. I'm going to take that 27, multiply it by 4, and I get 108. And then x, right? I have my 3rd, 2nd, but when we're multiplying them, that really means we should be adding them. So x to the 5th. And what that's equal to is our KSP value, 6.8 times 10 to the negative 29. So now I just have to simplify that, right? I'm going to simplify that up here. So I'm essentially going to take my 6.8 times 10 to the negative 29. I'm going to divide that by 108. And then to get rid of that 5 there, so I'm simplifying for x, I've got to raise this to the 1/5 power. And so if I do that, I have my 6.8 times 10 to the negative 29th. Wow, that is tiny. This stuff doesn't dissolve, essentially, is what that's saying. It's where our molar solubility is going to be so ridiculously tiny. And I'm going to take that answer and I'm going to raise it to the 1/5. And what I get is 9.1 times 10 to the negative 7. And if I'm curious, like, did I really do that right? Right? I could always take my answer, raise it to the 5th power, and then multiply by 108. I'm just going back and checking my work and I get that answer. So there we go. We know how many moles of this compound are going to dissolve in a liter of water, right? 9.1 times 10 to the negative 5th moles for every 1 liter. That's how many of these are going to dissolve in 1 liter of water.